When an incoming electromagnetic wave collides directly with a solid surface, it carries immense energy and incredible speed. A common misconception suggests that photons reflect by bouncing off materials, like tennis balls hitting a brick wall. In reality, light is an oscillating electric field. When it reaches a material, it drives the charged particles inside, specifically the electrons, into motion. These moving electrons produce new electromagnetic radiation. The reflected wave we see is the result of that coherent, collective re-radiation. This leads to a fundamental question. Why do materials with similar electron densities react so differently? A clear glass window and a silver mirror are both dense with electrons, all interacting with the same incoming light. Glass transmits 96% of that light, while metal reflects nearly 100% of it. To bridge that gap, we use the reflection logic chain. This roadmap traces physics from the quantum states of electrons up through the dielectric function and refractive index to calculate macroscopic reflectance. Macroscopic reflection represents the ultimate optical signature of how quantum electrons in a material are allowed to move. The process begins with the quantum states available to electrons. In a dielectric like glass, electrons are mostly localized in atoms or chemical bonds. Their filled valence band is separated from an empty conduction band by a significant energy gap. This creates the transparency condition. Visible photons generally lack the energy required to excite an electron across that band gap. Without the energy to jump the gap, bound electrons behave like driven harmonic oscillators. The Lorentz model treats them as if attached to quantum springs. This specific term represents the binding force. The electric field drives the electron, but this spring pulls it back. Metals lack this restriction. Because their electronic bands are only partially filled, electrons occupy extended Bloch states, allowing them to respond to even low-energy fields. We model this using the Drude equation. The defining difference is the absence of a restoring force. There is no spring pulling these conduction electrons back. Electrons in a dielectric are like people wiggling on springs. They can move, but they cannot run away. In a metal, the electrons act like a crowd that can flow collectively in response to a signal. The presence or absence of that single quantum binding force dictates the entire downstream optical destiny of the material. That freedom of motion determines our next step, the dielectric function. Because they are bound, dielectric electrons only slightly polarize. This modifies the speed of light within the material, but allows it to pass through. In metals, the free movement of electrons creates a massive current density. These induced currents produce fields that efficiently oppose and cancel the incident light. This effect is known as screening. This screening is effective up to the plasma frequency, the natural collective oscillation limit of the metal's electron gas. When light oscillates slower than this plasma limit, the free electron response is massive enough to overwhelm the vacuum contribution. Mathematically, this forces the real part of the dielectric function to drop below zero. This leads to the skin effect. Because the dielectric function is negative, the light wave cannot propagate. Its field decays rapidly within a tiny distance from the surface. A negative dielectric function is the mathematical translation of an electron crowd actively and aggressively rejecting a foreign electric field. This leads to our third step, the refractive index. The dielectric function dictates the complex refractive index, which is simply its square root. For transparent dielectrics, this index is mostly a real number, which controls how the wave travels and shifts phase. But because a metal's dielectric function is negative, its refractive index is forced to be dominated by the imaginary component, the extinction coefficient. This coefficient measures how strongly light decays inside the material. In optical physics, a high imaginary number represents a strict mathematical boundary that forbids light from moving forward. This brings us to the final calculation, reflectance. Reflection is determined by the optical mismatch between the air and the material. The law of reflection states that a material reflects more strongly as the difference between its index and air's index increases. Plugging in the mostly real refractive index for glass yields a very low mismatch. The result is that only 4% of the incident light is reflected. For metals, the massive imaginary index created by free electrons generates an extreme optical mismatch. With the wave blocked from moving forward, conservation of energy demands that nearly 100% of the light is redirected backward. The shininess of a mirror is the universe enforcing energy conservation when an electromagnetic wave hits an impenetrable wall of free electrons. This unified mechanism covers both materials. Bound electrons polarize and let light pass. Free electrons screen and force light to reflect. But real metals are rarely perfect reflectors. We can see this in the specific color of gold. Real metals possess unique quantum imperfections called interband transitions. Gold's specific band structure absorbs high-frequency blue light, removing it from the re-radiation. The remaining light is heavily biased toward the red and yellow spectrum, giving gold its characteristic hue. This proves the core thesis. The color and reflectivity of a material is a direct map of its microscopic quantum structure. Looking through a glass window or into a gold mirror offers a direct encounter with the macroscopic signature of quantum electrons obeying the rules of motion.